In the last lecture, we started the topic of machine learning, which is one of the main approach of artificial intelligence today. We also developed the basic understanding of the different concepts of machine learning, and also started one of the methods of machine learning, which is k-nearest neighbors. It turned out that this method is widely used, but also developed nonlinear models. In this lecture, we're going to talk about linear models, which has been widely used in statistics and machine learning for a long time. In this lecture, we're going to talk about two kinds of linear models. The first one is linear regression. We're going to talk about the history of linear regression that has roots in statistics. We're going to talk about linear regression with least squares, and talk about two methods of linear regression, one using matrix representation through the normal equation, and the second one is an iterative method using the gradient descent. We're going to compare both methods at the end. Second, we're going to talk about linear classification and present the method of the perceptron, its history, examples, and finally the algorithm. Let us first recall what is supervised learning. So suppose we dispose of training data. Training data is a set of examples that are feature values along with their labels. So we have this data, and this data is defined in RD, which is the space of the D features we have. We spoke about two kinds of supervised learning, regression and classification. In regression, we want to regress on a real value. So we want to be able to map the input values, which is the space of the feature values in RD, through to an output space, which is a real value. In classification, we care about mapping the input value into a discrete value, which is -1 or +1, which is the classification in the case of binary classifications, of course. Okay, so I'm trying to find models, and these models actually maps. These are the two models. One maps from the feature values into R, and the other one maps from the feature values into a binary into a set of binary values. Let us first start with linear regression, which is a very popular technique rooted in statistics. The most commonly used method in linear regression is called least square, used as early as 1795 by Gauss. It was later on reinvented by Legendre in 1805. Linear regression has been widely used in different fields, including in astronomy, to study the large scale of the universe. For example, find the regression that goes through most of the stars, or measure different distances, or estimate the distance between different parts of the universe. It is still a very useful technique today. So how does it work? Again, given a training data set of pairs of feature values labels, right? So the features are in RD, the labels are in R, right? We get used to this kind of framework. So we have, as we said last time, a set of examples, we have a set of feature values, and we have the label. The goal of regression is, again, to find a function f that maps the input to the output, the features to the label. We talk about linear regression because the regression model that we are trying to build, which is the function f, is actually linear because it can be represented by a linear function. For example, in the case of a data set with only one feature and one label, we plot this data into a two-dimensional space in which we try to find the best line that fits the data points. In other words, that finds a function that maps the y in function of x. So what we are trying to do is to find this line here that goes through most of the data points. The function is then a linear function in function of x, in which that we could write as f of x equal to the equation of a line, which will be a constant β0 plus β1 x. Right? So this is a line where β0 is the offset or the intercept. In the second example, we have data, in this case, laying into a three-dimensional space. We have x1, x2. We also have the label y. And we want to find some function f of x that is a combination of the function x of the features x1 and x2 that predicts best y, which would be, in this case, the hyperplane that you see here that goes through most of the data points in R3. In this case, the function of f of x would be something in terms of x1 and x2, which would be β0 plus β1 x1 plus β2 x2. So these two are the equations of a linear function. One is the first function is in R2, and the second one is the second function in R3. Let's develop now a method to build a linear regression model. So as we have seen in the previous example, a linear model is a function f of x that is linear in x, right? So we could write it in a more general fashion as f of x is the beta 0 plus the sum of the beta j xj, which means that we're going to sum over all the x features times what we call the weight or a parameter, which is beta. So for each feature we have a beta weight corresponding to it. In this case, learning the linear model means simply learning the betas of the equation, right? The equation that is actually the linear model that goes through the data points. One of the most used methods for finding these betas is called the least square, which uses what we call the least square loss. So remember, the loss is, so we build a function. This function tries to map the inputs to the output, but it's not a perfect function. So we try to see what kind of errors or how much we lose by using this function. Remember, we do have when we do a learning, in the learning phase, we do have the y labels, and we build a function that maps the axis to the y's. This function is not perfect, so we could compare the y that is the true label or the true outcome of the example with the estimated y or the function that is f of x applied to this example. So we spoke about the loss function that actually compares the true label to the predicted label. Predicted with what? With our function f of x. So in this case, a simple loss function would be to just do the difference between the true label and the predicted label, and take the square to not worry about the negative sign. Okay, so given this loss function, which actually, if we go back to our previous example, means that we are going to look at the difference between given a data point. Given a data point, we know for this data point what was the true y label, right? The estimated function at this point would be this value. So I'm going to take the difference between the true label and the function, which is the projection of the point on the function that goes through the data points. One of the methods to build linear regression models is called least squares. So recall in the previous lecture we spoke about the loss function, which is how much error is our function making. The way to know how much error or how good is our function is to see the difference between the true label versus the expected label, which is the prediction made by the function f, our model f. So we could do the difference between the yi and f of xi, which is the function applied to this data point. We square this, as we said, to avoid worrying about the negative sign in case yi is bigger or is less than f of xi, right? So recall in the previous example, we had we defined this function f of x, which is our f of x, right? This function. And what we want to do is to actually make little mistakes, which means that if we take a data point that has a true label y, right? And for this data point, when we apply the function f, we're going to get this point here. And we want actually this distance to be not big. So we want to minimize this distance, but we want to do it over all the data points in our examples. So what we want to achieve is to actually minimize the loss over all the examples. We want to be able to do as little errors as possible globally on all the data sets, right? So we define what we call the risk or the cost function, R, and this cost function is simply the sum of the loss values over all the data points. So we're going to iterate from 1 to n, where n is the number of examples. And so we take the risk over all those points. We divide by, so this is the average risk. We divide by 2 just for convenience, because these two will later on cancel each other when we do the derivations. Okay, let's take first the simple example when we have only one feature. So for one feature, as we have seen, we can write f of x as beta 0 plus beta 1 x. This is the equation of a line. We want to find beta 0 and beta 1, right? So the way to do it, so we want to minimize the cost function or the risk r, as we said, which is the loss function over all examples. So we're going to replace the function f of xi here by this value here, right, which is the equation of a line. which will make the risk function, which is a function of the beta values. This is what we want to find. We want to find the beta that minimizes the risk function R. Okay, so I'm going to replace f of xi by beta 0 plus beta 1x1 for each of the learning examples I, right? So with the sign minus, we will have minus beta 0 minus beta 1xi. And the goal is to find beta 0 and beta 1 that minimize this risk function here. So see how when we plug in the shape of the function f, which is a linear function of the feature x, right? We get this new risk function that looks like this. Notice that this function is a quadratic function. It will look like a ball if we plot it, just like shown in this picture. So the function will look like a ball with the minimum value of, or the optimal value for beta 0 and beta 1 will be at the bottom of the ball. So there is only one optimal solution that minimizes the risk in this case. So the figure on the left also shows another representations of the ball function with contours, where we see that there is only one single point for which we could get for which we have a beta 0 and beta 1 that minimizes the function or the risk function R. Okay, great. So let me introduce another notation. We talk about argument of beta of this risk function means that find the betas that minimizes this risk function. And this is our goal. How to find beta 0 and beta 1 in the case of one-dimensional space that minimize this risk function R. So we want to minimize a risk function R, which is a function of beta 0 and beta 1. To minimize this function, which means looking for this bottom of the ball function, we need to put the partial derivative of R at beta 0 to 0 and the partial derivative of the risk R at beta 1 equal to 0. So I'm going to do some calculations here. The partial derivative of the risk function R at beta 0 could be stated as this. This would be actually the derivative of this function. We'd see that the 2's will cancel. We are going to put this partial derivative at beta 0 equal to 0. This will bring us to this formulation of beta 0 in which we have beta 0 expressed in function of the y's, in function of the beta 1, and in function of the x's. So this is the formula for beta 0. We perform similar derivations to calculate the partial derivative of the function R in terms of beta 1. So we calculate the derivation of the risk function. We simplify the risk function and we set it equal to 0. This will lead to the formulation of beta 1, in which we plug in the beta 0, and we get finally a beta 1 that only depends on the data itself, which is the features and the labels. Given beta 1, we could always go back and plug in that into beta 0, and we also express beta 0 in this case in function of the data we have. So now if we have more than one feature, we're going to try to find a function f that is linear in x. So we have, as we said before, f of x is beta 0 plus the sum over all the dimensions, right, of beta j xj. Betas are the parameters. We need to find the betas that actually minimizes the risk function one more time, okay? So you could see that you have here in this case, so this is the loss per point. We're going to sum the loss over all the data points. But then for each function, we are just plugging in this function here. So we're going to go through the sum of the beta j xj for each data point and see how we are doing as compared to the true label. So this starts to be a little bit more complicated. Doing derivations on this function will be a little bit more complicated, and it's better in this case to switch to a more elegant way to write it, which is write it with matrices.